Good morning, everybody. I am very happy to present my work at the 24th RD Conference on Medical Image Understanding Analysis, Oxford 2020. I want to introduce my research paper entitled Radiomics, a new biomedical workflow to create a predict model. My name is Albert Comelli. I am a research scientist in nuclear magnetic resonance imaging and spectroscopy and biomedical imaging processing and analysis at the Radiomics Foundation. Now I want to introduce you my research work. Radiomics is an innovative and a promising biomedical approach aimed to provide quantitative information for biomedical images. These images features are used as biomarkers by relating them to physiological and medical outcomes of interest to identify any possible association between extracted features and the patient outcome or other clinical data. The aim is to identify personalized, predictive, and/or prognostic model to support the medical decision process. For example, among radiomics features that quantify tumor phenotypic characteristics, the heterogeneity seems capable to identify the treatment failure, improving the prediction of the patient overall survival and/or outcome. Radiomics is a fundamental application when computerized tomography, magnetic resonance imaging, or positron emission tomography studies are involved. These complex biomedical images contain a larger amount of quantitative information than cannot be quantitatively apprehended by the human eye. In the specific, hundreds of quantitative features from each tumor can be extracted from CT, MRI, or PET images. The proposed radiomics system is composed by the following 4 steps. In the first steps, the segmentation algorithm based on active contour is applied for each MRI study to identify the region of interest in a user-independent way. In the second step, the Mazda texture analysis software is used to extract radiomics features starting from the region of interest identified from the above-mentioned segmentation process, extracting a total of 290 radiomics features for each MRI sequences. In the first step, a novel mixed description inferential sequential approach is used to identify a subset of relevant features that correlate with the outcome. In the final step, the prediction model based on discriminant analysis is used to create a predict model in our patient dataset. Whatever the type of involved images, the proposed system to highlights the important step of a radiomic workflow. 46 patients who had been studied with MRI imaging were retrospectively considered to determine the absence or presence of the prostate cancer. MRI exams were performed using a 1.5 Tesla MRI scanner using the same imaging protocol in all patients. The standard clinical prostate examination include axial, coronal, and sagittal T2 weight turbo-of images of the prostate, axial T1 weight turbo-of images to exclude the presence of the hyperintense post-biopsy blood residues, and diffusion weight imaging. Diffusion weight imaging sequences were post-processed to obtain the apparent diffusion coefficient, MAPS. Histological examination identified the absent 0 or present 1 of the prostate cancer. In the first step, we used the pre-segmentation step implemented in previous work and adapted to MRI images. In detail, the region containing the target must be localized by the operator. Initial user input is required to rawly identify the area containing the target to avoid false positive. However, user intervention is minimal and limited at drawing a raw contour around the target. No future intervention is needed. A raw inclusion of the anomalous area is sufficient, based on the region highlighted by the user. The algorithm computers are using independent ROI surrounding the target using the region grouping method. This row segmentation identifies a ROI independent of the local variation in the initial user input, and for that, thereby making the result semi-repeatable. Starting from the operator-independent ROI, the segmentation is refined through the local region-based active contour algorithm. In the second step, we used Mazda software to calculate a future starting from the ROI obtained using the above-mentioned segmentation process, extracting a total of 219 radiomics features for each MRI sequences. Features are divided in first, second, and third order, providing information related to the gray level distribution within an ROI without considering spatial relation between the voxel first order, considering the spatial relation of voxel second order, and evaluating spatial relation among 3 or more voxel third order. Texture features are calculated from degree level histogram analysis, for example, mean, variance, weakness, kurtosis, and the percentiles, co-occurrence matrix, run leg matrix, and autoaggressive model, and velvet transport. In the first step, the dataset is composed of a X matrix with n row, number of patents, 46, and n column, number of features, 219, and of a Y vector of n values of a dichotomics variable, the gold standard, assuming values 1 tumor or 0 normal tissue. In our study, being the number of patents much smaller than the number of the struct features. Consequently, any classical statistical approach trying to deal with the X and Y data analysis without any preprocessing is not efficient. For this reason, we propose a novel mixed description inferential sequential approach to identify the most discriminant features and reduction the redundancy. The proposed approach consists of the following steps. The first step, for each column of X, calculate the point biserial correlation index between that column and the dichotomic variable Y, the gold standard. The second step, rearranging the columns of X by sorting them in the descending order of absolute value of point biserial correlation index. And the last step, start a will-do cycle. In this cycle, add one column at the time of the result X array, performing a logistic regression analysis. One of the output of the logistic regression is the p-value of the hypothesis test. The smaller p-value, the better logistic regression model interprets the variable of the response Y, gold standard. Compare the p-value of the current iteration with the p-value of the previous iteration and quit the cycle when it has not decreased. In the fourth step, the discriminant analysis is used to create a predict model in our patient dataset. We train the discriminant analysis to separate target texture radiomics features in two classes: no prostate cancers and prostate cancers. The training task need to be performed only once, and when complete, the discriminant analysis is ready to classify newly encoded radiomics texture. To generate the training input to the classifier, the result of histological examination are used as the gold standard. The key-fold cross-validation has been integrated. The dataset is divided into 5 equal subsets, and the holdout method is separated in 5 times. Each time, one of the 5 subset is used as the validation set, and the other 4 subsets are put together to form a training set. When the training stage is complete, the validation step is started to verify the performance in classifying new scenarios. Starting from a total of 46 ROI obtained using the proposed segmentation method, and from the 290 features obtained for each ROI using Mazda software, the most discriminated texture features selected using the novel statistic method described to certify the prostate lesion as cancer and no cancer were 3 for T2 weighted and 5 for ADC map images. This table shows the performance evaluation in the predictive model obtained using the discriminant analysis. In the specific, in the table is shown a comparison between the model obtained using all extracted features, first 2 rows, and using the most discriminant features previously identified in the last 2 rows. Finally, at the left, the figures show the received operating curves of the most 5 discriminant texture features for the diagnosis of prostate cancer on ADC maps. At the right, the figures show the received operating curves of the most 3 discriminant texture features for the diagnosis of prostate cancer on T2 weight images. In conclusion, in our study, the proposed radiomics workflow was able to identify targets using an operator-independent segmentation method, automatically extract 290 features for each segmentation lesion, select a subpanel of features with valuable association with the outcome, create a relevant prediction model for discrimination between prostate cancer and non-prostate cancer. We believe that our workflow can be useful to improve the prognosis evaluation, potentially allowing the personalizing of prostate cancer management. I want to thank Alessandro Stefano, Claudia Coronello, Giorgio Russo, Federica Vernuccio, Roberto Cannella, Giuseppe Salvaggio, Roberto Lagalla e Stefano Barone. Thank you for your attention and see you the next year in Oxford. Bye.